for ACURV. So initially we're a team from U of A. We're comprised of about 5 team members. This is Colin and myself. I'm Eduardo. And so over the past year we've been working on a underwater cooperative system. And I'll go very briefly into the background, and then we'll talk about this current design and where it's going in the future. So just a little bit on the background. So the idea behind this system is how to expedite very deep underwater missions. Well, our approach and our solution is to use theories in cooperative robotics that really involves having multiple similar vehicles that you can use both independently and as a whole. And by doing so, you can literally drop this the pod into the ocean or to this very deep environment, and the user can say if they want to use it as a big ROV, so as a big robot, or they can I guess decide whether to split off the group. And we're calling it autonomously cooperative because essentially what we want in the future is for the users to say, we want this group of robots to do a particular task. Then from that point on, the robots will decide among themselves how to do it. How many do you need to do this task? So that's where the autonomy comes in. So in any design of any particular engineering project, you have some requirements that you need to go through. And these were our main requirements for the individual ROV or the individual module. So in this thing, we wanted a vehicle to cost under $5,000. We wanted easy to transport, easy to be reliable, etc. So these were our requirements. And in order to arrive at the particular design, we went through, it's called the House of Quality. If you're not familiar with it, it's just a method of converting qualitative, like adjectives, like being easy to reliable, easy to transport. You use those adjectives in fine technologies. For example, a technology would be an underwater camera. It would be a computer on board. It would be your tether. So those are technologies, and you take your adjectives and you really cross-reference them with your technologies here. So for example, I mentioned camera, or battery, all these, and you come up with the technologies that are most crucial for your design, right? So you have to weigh your technologies. You come up with, we came up with a couple of values that I'm not going to go over, but basically we found that, for example, our tether was very crucial. A good tether to the success of this design. A good stable platform was very important. So yeah. So this is just the cross-referencing part. Yeah.
So this is the design that we decided on, and it was to, in the future, if we were to have 6 cooperative robots, we were to have one surface computer controlling all of these 6 robots, each having their own computer, which would be easy to get data to and from them, and for them to communicate with each other. And, so that would be the future. And this is the GUI that we currently have on the surface that feeds back all of the information on the robot. It has things such as the status of the robot with those 6 LEDs, the actual tilt and roll of the robot as well as its heading. And each motor controller itself is outputting the input voltage, the temperature, and the power that it's set at, as well as the status of it. And we also have things such as analog sensors for pressure and temperature, and then the numerical display of the roll, pitch, and heading. And here's a view of our robot. And then here's some of the sensors that we used on the robot. The upper left is the pressure sensor. 0 to 30 psi. And then we also have a camera, which we didn't actually use that one anymore. We replaced it with a BNC camera. You can see it right here. And this, it feeds back up through the tether to an RC cable. This is the sensor board right there, and that was, we basically took a bunch of breakout boards and fabricated another board to stick everything onto, to get rid of some of the wire mess. So that's where we have things like the inertial measurement device, and then the temperature sensor, and then 2 analog to digital converters for our pressure and temperature.
So moving on to the thrusters, these are not off the shelf, but we customize all the thrusters. So each thruster has a total of about 20 parts that were fabricated and machined. We're using off-the-shelf DC motors and off-the-shelf propellers. Everything else was made. And the advantage of making it was really cutting down cost. It cost around like about $80 to make the thrusters at the end, versus commercial ones that are like around, $500, $600. And the other advantage is that we could really customize from the beginning the design of these thrusters to fit our system. There's a structure, just a little about the mechanicals of it. The structure is made of ABS plastic and aluminum. That's pretty much all where we stick to. And I can show you very quickly. So, move on to the next. Yeah, a couple of the crucial things is the choice of material. Here on the ring, this is fabricated out of aluminum, as well as this red plate, which is on the next. So this top dome, this cylinder, or this plate, everything is machined out of aluminum, and it's hollowed out in order to make it lightweight. And this is where we house all our electronics to run the vehicle. And we try to keep everything, again, off the shelf and compact, so if something fails, we can replace it.
The last thing that it was showing was the power supply box, which our original design had a 120 volt AC to 12 volt DC converter on the robot, and it was tested and it worked perfectly, but it wasn't designed for the competition, so that's why we spent the last few hours actually changing it out with some nickel metal hydride batteries.
A little bit in conclusion, we just have some rough numbers of time spent, and the general numbers that people are interested in. The quick facts are that lines of code we use, a part count, but obviously the most specific, what it was designed to, as far as depth. It was designed to go 40 feet in depth. Most of the parts were modeled in SolidWorks, and we placed the forces on them, and to see how they would deform under I guess the pressures that we were estimating. And this is just a quick layout. These are most of the parts that go into the vehicle. One thing that's not included is the robotic gripper. Currently, we've tested and tweaked this around, but it was finished last minute. And for the competition, we're cutting out the third motor that gives you the third degree of freedom, which is this motor, brings it up and down. So we're cutting that one